It's a pleasure to be here today. Let's see, I hit the enter key, right? Okay, I'm going to dive right in since I have a lot of things to show you and not a lot of time. But one of the things that's very important to understand is that launch costs are way out of hand. They're scary. That's what the graphic is supposed to mean on the right. People have asked, in fact, someone this morning asked me, what would it take to get P3E into orbit? And it's actually quite simple. It would take $10 million, in euros, of course, but roughly $10 million. And that's why P3E is sitting in Marburg and not sitting in orbit. For ham radio, that's an unrealistic number. But even a small satellite to LEO is around $3 million today if you have to buy a launch. $3 million. ARISAT, some of you may remember the ARISAT satellite that we put up last year. 2011, yeah, I'm off a little. 2011, I asked NASA, I called them up and asked, what would it cost to fly another one? Just give me a number. And they told me, oh, we'll give you the EVA for free. Give us $1 million and we'll launch it. So that's kind of an unrealistic number for something like ham radio and especially AMSAT. A microsat to LEO like AO51 would cost around $500,000. So these should be scary numbers. If they're not scary, come to the AMSAT booth and we'll talk to you about putting some of these satellites up. So even a 1-unit CubeSat to LEO at the bottom there costs around $100,000 today. That's a lot of money. That's within the range of realistic for AMSAT, but it's still a lot of money for us to raise. So we'd like to avoid these costs because these are scary things. Okay, so we need to have a launch strategy that helps avoid those costs. And what are we doing? Well, what we're trying to do is take advantage of the large and growing interest in CubeSats. Every university in the country that has an aerospace program is interested in CubeSats. But NASA is also interested in CubeSats. The National Reconnaissance Office, who makes those spy satellites, they're interested in CubeSats. Boeing is interested in CubeSats. The entire space industry is actually extremely interested in CubeSats. And so AMSAT's decided it's time for us to be interested in CubeSats. So our strategy is to develop a family of CubeSats that would be interesting to universities for flying science experiments. And that those CubeSats, unlike typical university satellites, would include ham radio transponders. And I mean two-way voice communication transponders, or maybe CW. But not just beep out an X25 packet and we're done with that. Because some people find it interesting, but that's not the normal sort of ham radio that we're used to. And we're going to partner with those universities to develop joint science and education missions and make proposals to NASA for a free launch, that's a free as in $0 launch, via the ALANA program. ALANA is the Educational Launch of Nanosatellite program. So that's been our strategy. We have two program phases. We're going to start with 1-unit CubeSats, which is a 4-inch cube. If you're not familiar with that, stop by the AMSAT booth and we have a mechanical model of our 1-unit CubeSat. That CubeSat would do FM analog repeater like AO51, as well as high-speed digital data up to 9,600 bits per second raw, or about 8,000 bits per second with forward error correction. And then our plan is to move on from there after building about 4 Fox-1 satellites into our Phase 2 satellites, which would have programmable transponders, which would support a variety of modes, including linear transponder modes or even higher speed digital modes. And that's done through a software-defined transponder. So how about Fox-1? So I'm going to cheat and move ahead a little bit. See the yellow? See the yellow? Scheduled for launch in November of 2014 on the ALANA 12 mission. So we wrote a proposal to NASA in November of 2011, and it included a MEMS gyro experiment that we had sponsored at Penn State University as a science experiment. And it included the statement that the ham radio transponder itself was a STEM education activity as our primary mission. And that proposal was accepted in February of last year into the Alana program. And did I point out that we're now scheduled for a launch on that program? Can you tell I'm excited? So our launch will be, the orbit that NASA's told me we have so far is about 470 by 780 kilometers. So that means apogee will be about the same as AO51, which means coast-to-coast, east-to-west coast coverage with an FM HT. And the orbit lifetime is about 11 years. That depends on what the sun does, but it's not a short-term 12-week lifetime or a couple-month lifetime. It's an 11-year lifetime. Okay, I'm going to do a very quick technical overview of the satellite. This is a block diagram of the entire satellite. It has solar panels that feed a power supply card. That runs a battery, charging the battery in the sun and allowing the satellite to operate off the battery in eclipse. The IHU card is the brains of the satellite. That has a main processor on it. That talks to the science payloads to allow exchange of data. And it formats the data, the telemetry and the data down to the RF cards. There's an RF receiver card that has an FM radio and an RF transmitter card that has an FM transmitter. We come in on 70 centimeters and come down on 2 meters. Here's a couple of pretty pictures. This is an actual solar panel. These are gold-plated. We use these ultra triple junction solar cells that are 28% efficient. They're not state-of-the-art, but they're very close to it. They're 28% efficient. That's very, 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 very good. And they're rad hard. They're made by Boeing, which is a Spectralab market name. We get about 2 watts on each cell, on each panel, excuse me. So this is what the power looks like in orbit for the worst case eclipse. And that, while you're in eclipse, of course, you get no power from the solar cells. And then you can see it goes all over the place from each of the sides until we go back into eclipse. But in general, we're above 3 watts when we're in the sun, and of course, no watts when we're out of the sun. And that gives us something around 2 watts average power for the worst case. There are some parts of the orbit where we are never in eclipse. It's always in the sun. Okay, the power supply card takes that crazy, wildly varying solar illumination and converts it to power on the power bus. And we use these devices called maximum power point trackers to extract the maximum power we can out of the solar cells. And you can think of them as impedance matching devices for DC. They're not really antenna tuners, but they're kind of like, they have the same kind of function. They tune the solar panel, the battery requirements to what the solar panel can provide as best as possible, and does that automatically. And the reason you need that is, if you look at this picture here, the bottom red line shows the amount of power you get out of the cell versus the amount of current you try to draw out of it. And you can see that the power increases up to a point and then very quickly goes down to nothing. So the optimal spot to operate the solar cells is at the peak of that red line where it just crosses over the 1 watt level. So that's what we want to do, is constantly run our solar cell transmitters at maximum power, just like all good hams. The Max PowerPoint Tracker is basically a DC to DC converter with some fancy tracking and feedback added that allows you to do that. Unlike a typical power supply, you don't regulate the output voltage, you regulate the input voltage. And here's a test circuit that shows that we can do that. That's a TI demo card of a DC to DC converter with a bunch of parts added. So of course our challenge is we have to put all of those parts, 6 of them, on one of our little 4-inch by 4-inch cards. The battery card. We have 6 A cells on a battery card. An A cell is bigger than a AA. They're widely used in Model RC toys, and so they're widely available. They have higher capacity than the normal size NICADs that you're probably used to. Our batteries, the 6 batteries, have 12 watt-hours capability. And by having that large capability and only using a small part of that, we expect to get very long lifetime out of our batteries. We also have active thermal control, meaning we control the temperature of the batteries so that we don't harm them during our normal operation. We were intending not to overheat them or charge them when they're too cold. And the battery card also has the telemetry processor and those little gray rods on the side. You can see one of them in the front is the hysteresis rods for stability. That's just a convenient place to stick them. We did work up a battery test. This is to actively control the temperature of the batteries. Dick Jansen did this, if some of you guys remember Dick. He put this together, and this is currently being wired into a vacuum chamber for test. The IHU card is the brains of the processor of our satellite, as I mentioned. We have, it collects the telemetry, it runs the science experiment, it can do high-speed data by generating the bits in software, and it executes the commands from the ground. It's an STM32L microprocessor, which is 32 bits, pretty powerful, 32 megahertz. And we actually bumped these numbers up. We now have 384K of flash and 48K of RAM, because you can never have enough flash and enough RAM, right? So, and we put the MEMS gyro experiment from Penn State on the IHU card. So we have these little tiny gyros that can detect our rotational motion in space, and that's going to be an experiment to see if they work okay in space. Here's a picture. B. Dale Garvey, I don't know if you guys, probably some of you know him. B. Dale has been working on this card, and he produced #1. You can see it's lots and lots of little tiny parts. And a big chip in the middle is the processor. IHU Software, we have a software team that's developing the code for this thing. It's now running on that card, and you can see a demo in the AMSAT booth. If you stop by, you'll see our operating system. We're using free RTOS, which is free as in the name. That's because that's what we like to pay for things. And that's running in our engineering booth. So stop by if you want to take a look to see the card. The RF receiver card, it's a 70 centimeter FM radio. It has a low noise preamp on the front, so it's very sensitive. You'll be able to easily access the satellite with 2 watts and a handheld beam, as long as the guy next to you isn't running 100 watts in a handheld beam. And it has automatic frequency control to help automatically correct for Doppler at the satellite. So it will reduce the need to do Doppler correction on the ground on the 70 centimeter band. And here's a picture. We have this running. The big card, I don't know if I can, my mechanical laser pointer doesn't quite reach over there. But the big card is basically a cell phone. We took a 900 megahertz cell phone chipset and converted it to run on 435 megahertz. And that's a pretty sensitive receiver all by itself. But we also added that strip on the side, and that's a low noise, 1 dB noise figure kind of preamp. And off on the right, off on the top is a phase lock loop to generate the local oscillator signal. So this is actually working right now. Our challenge will be to take these circuits and put them on the 4-inch cards. The transmitter card is 2 meters, it's FM, and our power amp produces about 400 milliwatts just at the point where we can barely operate. That's like 3 volts on the battery. At the maximum battery voltage, we can produce around 800 milliwatts. So on 2 meters, that should be a pretty booming signal from the satellite. You should be able to work the satellite mobile and hear it without any problem. And here's a picture. Here's a picture of the PA. This is working. We don't have this here because we only have one of these, and I didn't want to risk it. But this is a working prototype of the power amp. It's also about 70% efficient at maximum power output, which is pretty darn good on 2 meters, especially for one that works on 3 volts. Attitude control, we use the old AMSAT standby of passive magnetic stability control. We have a bar magnet integrated with the frame and those hysteresis rods on the battery card that do motion damping. So the satellite antennas will be lined up with the z-axis of the satellite to prevent QSB from tumbling. You should be able to get a fairly solid, non-fading signal from the satellite. Here's what the antennas look like. They're actually just simple whips made out of beryllium copper spring wire, and they just spring out when we release them from the CubeSat. So experiments. We actually have 3 experiments running on Fox-1. The MEMS gyro experiment is to measure the rotation of the satellite using a MEMS sensor, and that was the Penn State experiment that we had funded for the senior design project. But since we had space on the satellite, we decided to add some more experiments. We added the low energy proton experiment from Vanderbilt University. In a nutshell, that's an experiment to help us predict how often electronic parts will have bits flipped in orbit. And that's a useful thing because it helps us to predict how often will a processor do a sanity reset because a low energy proton whacked it and knocked its program counter off into hyperspace, for example. So this is a useful experiment for us. Vanderbilt uses it to make prediction models, computer prediction models. And they're providing that experiment. And then there's the JPEG camera. We've added a camera from Virginia Tech. Bob N4HY and his guys, his grad students, are putting together a camera. We have a demo of both of those experiments, as well as the MEMS gyro, in our AMSAT engineering booth. So if you want to take a look, stop by and you can take a look at the camera. The camera has VGA resolution, which is about 4 times what you would get with slow scan, and the images are sent down digitally with error correction. So the images should be crystal clear, color, VGA quality. We're very excited about this experiment. Here's what the LEP experiment looks like. That's from Vanderbilt. You can see they've actually built the card, although they're missing a RAM chip at the bottom. And here's a slightly out of focus picture of the camera card, not taken by the camera card. That was Bob. He's a little out of focus there. And then when you put the whole stack together, this is what the electronics look like in the satellite. The RF transmitters at the bottom, then the receiver, the IHU, the power card. The batteries are double size, if you will. It takes 2 spaces because of the size of the batteries. And then the experiment cards. The structure is actually a very ingenious design that Bob Davis did. It's a pair of bent sheet metal clamshells that screw together. So it's just bent sheet metal. It's aluminum. When you put it all together, it looks like this. And the gold color is because the solar panels are, in fact, gold-plated. And there's 6 solar cells, 2 on each side. You can see at the bottom and the top on the right the spring wire antennas. The antennas just wrap around those posts while it's in the rocket ready to launch. And then they spring out. They're released by the little resistor at the bottom, you can see, melts a piece of plastic nylon wire, and the antennas spring open. So it's very simple, and yet they're decent size. It's about a dipole on 2 meters, and it's actually a little bit bigger than a dipole on 70 centimeters. Fox will have 2 operational modes. The transponder mode is the normal FM repeater mode that you're all familiar with. In order to save transmitter power, we actually send the telemetry and experiment data from the low energy proton and MEMS gyro experiments as low speed FSK in the subaudible band. It works very similar to DCS, if you've ever seen that button on your radio. So we send the data below the audio band so that we can send it without having to have a separate transmitter for telemetry. And then in camera mode, it'll use the entire bandwidth to send the camera pictures. It takes about 50 seconds or so to send an image down. And that's the high-speed data mode, about 1 photo per minute. And we'll also send the telemetry and experiment data along with the image data. Did I mention that we have a launch in November of 2014? So this trick worked pretty well. We're very excited about this satellite, and we decided, we're planning on building 4 satellites. Maybe we should try this again. So what's next? Well, it turns out that I wrote another proposal for a second Fox-1 satellite, and that was, it uses a Fox-1 satellite bus. This one has all of the experiment cards supplied by Vanderbilt University, their space radiation experiments. And the experiment, one of the good things about radiation experiments is they don't use very much power and they don't generate very much data. So we can run the experiments along with the ham radio transponder. You don't have to turn one on and turn one off, you run them all at the same time. So this was proposed last year, and NASA accepted us into this program in March of this year. So we're in the program for a second satellite. We haven't received a launch date yet. And Alan's saying I have 5 minutes, so I'm doing okay here. I have to show this sign. Of course, AMSAT is all volunteers. AMSAT doesn't pay well, so AMSAT is always hiring. So if you're interested in analog circuit design especially, but any of those design engineering, satellite construction, or testing areas, any types of engineering associated with satellite development, if you're interested, stop by the AMSAT engineering booth or send me email, aa2tx@amsat.org, and I'm sure we can find something to sign you up for. Okay, any questions? I got about 3 minutes, I think. Yes, Blue? The mass of the CubeSat is about 1.33 kilograms, which is about a little less than 3 pounds. Yes?
So AMSAT's designing all these different circuits. What evaluation does the government put on any of the intellectual property that's being generated as a result of all this stuff by AMSAT?
Okay, so the question was, what claim does the government have on the intellectual property, since all of this is custom designed by AMSAT volunteers? And the answer is none, thank goodness. AMSAT will own all of our intellectual property.
What was that the government claim? How does it affect getting funding when AMSAT's generating this kind of?
Yeah, so the government doesn't fund any of this. It's not funded. Another question? Yeah, Pat?
How severe is the rotation of the satellite expected to affect the clarity of the VGA image?
Okay, so the question was, how fast does the satellite rotate, and will that affect the VGA clarity of the photos? So the satellite's expected to rotate around a half an RPM to an RPM, in that range, and that is not expected to have any impact at all on the VGA clarity. It's slow enough that it won't matter. Yes? I'm sorry? How often will pictures be taken? About once a minute. We'll take a VGA picture, a snapshot, about once a minute. It takes about 50 seconds to send the picture down. Any other questions? All the way in the back. Yeah.
It's satellite is in orbit. It will be available for communication as soon as it's commissioned.
Okay, so Jay asked about when will the satellite be commissioned, or how long after it's commissioned will it be available? And we expect that we probably want to run through a bunch of tests for a week or something like that, and then there's no startup time on the satellite. It's basically ready to go. So we would, as soon as we launch it, we'll start running tests, make sure everything's okay. As long as everything's okay, the repeater will be ready to go and start making contacts. Yes? Is there a beacon? So the question is there a beacon? There's not a separate beacon. The downlink, which is the FM, if there's no activity, which typically does not happen over North America anyway, the satellite will automatically turn the transmitter on every once in a while and do a voice ID, just to say, hey, I'm really here. But typically over Europe or over North America, that's not going to happen. Maybe over the Pacific Ocean someplace. Pat, yes?
Could you mention a bit about the command stations we'll be using? How often will they have the satellite offline? Or
Okay, so the question was, how long will the command stations have to play with the satellite? We don't expect them to have to play with it at all, other than scheduling the transponder mode versus the camera mode. This satellite does not require a bootloader. It doesn't require uploading software. If for whatever reason the processor crashes, it comes back automatically. There's no, it's expected to be very low load on the command stations. Okay? Alan, how am I doing here?
1 minute.
All right, I got over here blue. Will the footprint be big enough to hit Hawaii? So that's a loaded question, you know. So from my house in Boston, it's not long enough to hit Hawaii. I'm going to have to see what we can do about that. But from California, you will certainly be able to hit Hawaii. Yeah. The question was, what kind of command capability do we have? We do have a command uplink, and the command stations, which there are a handful of trusted stations that will have the command codes and the authorization codes, as well as the special software needed. We'll be able to control and monitor the batteries and control the battery usage from the ground. Let's see, all the way in the back there? When would you expect the second satellite to launch? So we asked for a launch for the second satellite in the second half of 2014, and NASA actually has already talked to me about what orbit we preferred, but they have not promised us a launch date yet. So I don't know the answer to that. It's a hard question to answer.
What kind of orbit altitudes are you talking about?
Okay, that was on my other slide, but I'll repeat that. The orbit altitude, the max altitude is 780 kilometers. That's the apogee, and the perigee is 470 kilometers. So, like I said, at apogee, it'll be roughly the same as AO51. At perigee, it'll be a little higher than the ISS. All right, Bill, you're the last one.
What's the inclination of that sort of thing?
Oh, the inclination, I'm sorry. I don't know if I had them on there or not. It's 64 roughly degrees. So it's a good orbit. It's an excellent orbit, actually. In fact, it's the orbit we asked for. Can't beat that with a stick, right? Thank you all. Thank you very much.